Okay. Okay, so welcome everyone to this week's talk in our QTFMS series. So we are very excited to host Xingyang Yu, who is a postdoctoral researcher at Virginia Tech University. He will talk about his work on non-invertible symmetries via von Neumann subfactors. So Xingyang, thanks a lot for accepting our invitation. It's a pleasure to have you, so you can take it away.
Okay, thanks. Thank you for the nice invitation. As we introduced, the title is Non-invertible Symmetries, Velvet and Subfactors. Basically, I will talk about how to use a very well established mathematical tool. It's basically based on the fundamental algebra structure to capture certain structures in the fusion category, which nowadays is already known to be the right language for describing the unitary finite symmetries in two-dimensional quantum field theory and even some lattice models, at least in the continuum limit. So this work is based on the joint paper with Hao Zhang. Paper is all right. And this is the abstract. So if you want to read it into details after my talk, and if you have any comments and questions, just feel free to ask me. And of course, during talk, if you have any comments and questions, please do not hesitate to stop me and ask me. And now I'm like in China, so it's kind of, I'm afraid that during my talk, I will be like, sleepier and sleepier. So if I say something crazy, please let me know.
I wish
Okay.
if you were to told me that you were in China, we could have rearranged the date or the time.
It's okay. It's okay. No, no, no. It's
Okay.
okay.
I mean,
It's fine.
I thought you were at Virginia, so
Yeah.
that's
Yes.
why.
Right. Yes. Yeah. Yeah. For most time, I'm still, but it's totally fine for me. So it's fine. Yeah.
Okay.
Just
Okay.
no worries. Okay. So why do we care? That's almost everyone. The first part of the talk. So the motivation nowadays we already know that non-invertible symmetry is very important. So let me just write a name here. Non-invertible symmetries. Sym Symmetries is like important. Okay, let me give an example. For example, you can think of how it play with the order flow. So non-invertible symmetries from the first glance is not really a symmetry. Sometimes it is not even preserve. I mean, for most of the cases, it doesn't even preserve the vacuum. I mean, the norm of the vacuum of the Hilbert space of your physical theory. But still, it has very interesting properties, which are shared by the ordinary symmetries. Let's say if you have a non-invertible symmetry and you can again capture, you can like ordinary symmetries, you can capture its anomalies, and those Toft anomalies will be the RG invariant. So you can generalize the notion of Toft anomaly matching from the UV to IR in terms of the non-invertible symmetry. So of course you can say much more stuff in your theory. Let's say you have some 2D theories or you have some higher dimensional theories that's nowadays it should be all fine. I think people is well believe it's like widely believed that it should work in any dimensions. You have the theory which does not even have any non-trivial invertible symmetries, but you can still find some non-invertible topological defect which give you topological symmetries, and you can capture its Tooth anomalies in a generalized version or in a generalized notion. You can say more things about what is the infrared phase of that theories. So that's one of the most important applications. And of course, there are many other more applications. So in this talk, of course, I will trying to say something about those other applications and show how to extract those physical results from the mathematical tool.
Can I ask a question?
Yeah.
So when we have an ordinary symmetry, we can turn on some background fields, and that's how we capture the Tooth anomaly. But in the case of non-invertible symmetries, it's not very easy to, turn on some background fields. How do we detect that Tooth anomaly?
Yes, you're absolutely right. So there are multiple ways in the invertible case, as you said. No matter it's continuum or finite, you can always turn on background field. Sometimes it's differential forms, sometimes it's differential cochains, and you see the phase ambiguity of the partition function under the symmetry background transformation. And that phase ambiguity, of course, is the Tooth anomaly. In non-invertible case, it's a little bit, you need to try to go around, like you should not expect you have the background field description, but you can use some kind of construction nowadays known as SIM-TFTs, but it has a long history. Nowadays known as SIM-TFTs. You can try to extract the symmetry information from the QFT into one-dimensional higher bulk. And there are some constraints of the topological boundary condition on the other side you should be able to pick or not. And those
I
abstraction of
see.
picking topological boundary conditions will capture the anomalies of the symmetries
I see.
because changing topological boundary is gauging. If you cannot
Mhm,
pick some topological boundary, it's abstraction to gauging. So that's tough
mhm.
anomaly.
I see. So the SIM-TFT for
Uh,
non-invertible symmetries already captured the Tuft anomalies.
exactly,
Okay, okay.
exactly, yes. And in 1 plus 1D, we're luckier because in 1 plus 1D, everything is nowadays formulated into the fusion categorical symmetry language. So you can just check whether you have some allowed algebra object so that you can do the gauging. If some of the algebra object, or let's say subcategory, cannot be summing over as topological operator insertions in the 2D worksheet, then it cannot be gauged. There are some very abstract way to do that, and I would say it's like more formal and precise than the SIM-TFT description. Sometimes it's very quantitative. It's not just qualitative. It is because it is all encoded in something called the F symbols in the field category. But I will capture some of those properties in the following.
Okay, thanks.
Okay, so in 2D, as I said, we're lucky. We have many, many examples of non-invertible symmetries, even back in the days when the word non-invertible symmetry is not, sorry, when the phrase non-invertible symmetry is not invented yet, especially in the context of RCFTs. So for, let's say, the simplest case, you have a diagonal RCFT. So you know that basically all the information of this RCFT is encoded in the local vertex operator algebra, or you just say that I have some chiral algebras which have some primary fields. So for every primary field, let's say I have the primary field, which is just some local operator, it should be one-to-one correspondence to the validity lines of the RCFTs. Those validity lines, in general, will obey some non-trivial fusion rules, which is not just group multiplication law. Okay, the validity algebra is way more complicated than that, or way more general than that. So back in those days, people just call them, oh, this is validity lines, and they obey some fusion rules, or they obey some validity algebra, but they don't really call those as non-invertible symmetries. But now we know those are the very first examples, one of the very first examples of non-invertible symmetries. And then you can consider more and more complicated CFTs and even QFTs, which is not conformal. You can also think of some topological phases. You can also think of some TQFTs, which is protected by some non-invertible symmetries. Okay, by some non-invertible symmetries. Let me just don't write the info to save time. By some non-invertible symmetries, and then you can try to use a very formal language to axiomatically construct the TQFTs. When I say axiomatically constructed, it means that all the input you use is the symmetry structure, and in the end, the output is the TQFT, which obeys the Atiyah-Segal axiom for TQFT. Okay. And then there are some key questions about non-invertible symmetries when we try to generalize the invertible case. One of the key question is, for the invertible symmetries, if it is non-anomalous or it had some non-anomalous subgroup, we can do the gauging. When we do the gauging, we're really doing some not local, but some topological or global manipulation of the theory. Especially in the CFT, we can do everything very very complete and precise because we know the CFT has very nice quantity is the torus partition function, right? Basically, all the information of the CFT, at least bosonic CFT, is encoded in those torus partition function. And there is a very precise way to capture what is the partition function of the gauged theory for the ordinary symmetry. So the question for non-invertible symmetry, That's one of the most important motivations, is how to gauge non-invertible symmetry. Is there a universal way? And what is the result of gauging non-invertible symmetry? The other motivation. What is the topological phases? Sorry, what are the topological phases enjoying the non-invertible symmetry? Very abstractly, if I have a gapped phase, which adds some, we can consider some gapped phase, which adds some infrared phase of some field theory or lattice model, but I would like to know how these gapped phase are arranged under non-invertible symmetries. Okay, for the invertible case, I know there should be SPT, SSB, all kinds of other things. I can say different things about particle excitation, about soliton configuration. What can I say? For those phases and their topological configurations or local excitations under the non-invertible symmetries. Those are the two main motivation for me. And this is embedded in the context of CFTs. This is, of course, embedded in the context of TQFTs, or let's say solitons. Because we all know soliton are topological configuration, they're not really propagating local excitations because it transits between different vacua. Okay? This is why in my title I say I have conformal and topological applications, and I will elaborate on this point more. Any
Can I
questions
ask a
about the
question?
motivation
Yeah.
and background? Yeah.
So if you know the SIM-TFT for the non-invertible symmetry, then we know how to gauge it, at least in the sandwich construction, right? Because it's the choice of different topological boundary conditions.
Exactly. Yes. So in principle, if you know the same TFT and if you know how to capture or classify all its topological boundary conditions in 2+1D SIMTFT, that's just capturing all the Lagrange algebras. In principle, if you can do that, then you have basically all the answer. But as I will say in the following slides, that's always easier said than done. That's why we need phenomenal subfactor to really give you some results. If you really want to deal with some complicated non-invertible symmetries instead of just rep-deep for which everyone nowadays know how to do it.
I see. And
Yeah.
I think in the context of 2D CFTs, the SIM-TFT is usually something like a trivial TQFT, right?
Right, it's basically the triumvirate TQFT of that fusion category.
Okay.
Or you
So
can just say
understood.
that the center of the fusion category.
Okay. Yeah. Okay.
So
So
basically, yeah,
understanding the Sorry.
yes.
So understanding the topological boundary conditions of trivial TQFT is basically understanding how to gauge non-invertible symmetries in 2D
Yes, yes,
CFTs.
yes. Yes,
Okay.
exactly. Yes. Classifying the Lagrange algebra of the SIMTFT is the same as classifying all gaugings. And in the TQFT case, that's also classifying all the topological field theories, as I will said
Hmm.
in the following slides. Yeah. Thanks. Other questions about the motivation and backgrounds? Good. So non-invertible symmetries in 1+1D. For those who are already familiar with this context, I apologize because this might be very trivial to you now. But let me just go over it for completeness. In 2 dimensions, now we're considering just the zero form symmetries. Okay, of course, in general, you can think of -1 form symmetry, zero form symmetry, and 1 form symmetry in 2 dimensions. When I say 2 dimension, I always mean 1+1. I'm a Heinrich theory person. So we don't consider -1 form symmetry here. We don't consider 1 form symmetry here. They're both very subtle, okay? Because -1 form symmetry is basically just something living in the parameter space, but I just want to focus on a certain theory. 1 form symmetry usually leads to decomposition of the theory, right? I have like sum over different theories. I just don't want those weird or subtle structures. I just want a well-defined QFT with a single vacuum, okay? So I consider zero form symmetry, non-invertible symmetries, and then everything is defined by codimension 1 topological operators, which are lines in 2D. And then for every local operator, they can be charged. Of course, trivial charge is also can be think of as some kind of charged. So for any local operator, you can have this kind of configuration. You can have the line linking or surrounding of this local operator. And after that, you are mirroring the charge of this local operator under the non-invertible symmetry generated by the topological line. So this is what I called O prime. It's just after charging this operator. And then for this topological line operator, where I labeled by LA, topological operator, I labeled by LB, you can do the fusion of these two topological lines. In the end, you will have a weighted sum of topological operators. This is in general called the fusion rules. As you will see, as you can see easily, if there is no sum here, you just have a single local operator here, single line here, and a single line here. You can recover the group-like case. Okay, let's say you have LG, LH. In the end, this will be just LGH, when G and H is just some group elements. So this will just recover the group-like case. Okay, so if you have the group-like symmetry, all the fusions of topological lines will obey the group multiplication law. So it's always invertible. In other words, if you have this kind of multiplicity on the right-hand side, you should expect that you have a non-invertible symmetries. And then you have this very weird associator structure. Okay, if you do the associative move, you can see that you are not expecting always have the trivial result. The associator move sometimes it's a non-trivial isomorphism, and it is labeled or it is captured by the F symbol. You don't need to really worry about all these letters. I'm just making this trying to be complete. Okay, so basically you can think of you just need to make every label play their role in these F symbols, but in the end what you do is just when you do the associator move, you see a different result. Very
Can I ask a question
schematically
about this?
speaking, yes.
Uh, at the slide, you talk about that in when we consider fusion rules and when there is a coefficient on the right-hand side, we can say that you said that we have to consider non-invertible symmetries. So in the, for example, Fibonacci onions or maybe Ising onions, we have, for example, these fusion rules for specific particle species. So can we say that, or what is the necessity conditions in such fusion rules implies non-invertible symmetries?
I think as long as it's not like the group, like as long as it's not the group multiplication law, then it is non-invertible. Like you have the complete set of topological line operators you want to consider, and you check every single fusion rule between every two lines. As long as one of those are not group-like, then it is non-invertible.
Oh, okay. Thank you.
Yeah. Any other questions about this page? Okay. Now let's move to two things we are interested in for today. Okay, I'm saying that I will take you into the world of conformal and also another world of the topological. So in the CFTs, we can do very precise on gauging. We can talk about what is the partition function look like, and we can check explicitly what is the quantum symmetry after the gauging in the sense of Krumrov and Waffa's very old paper. If you have a ZN symmetry for a CFT, you do the gauging. In the end, you have a dual ZN symmetry. Okay, so let's just take the very basic information. What do I mean by gauging in CFTs? So consider gauging in CFTs. The simplest example is just the simplest non-trivial example is the Z2 global symmetry. For a theory T, which is a 1 plus 1 CFT, you can gauge its Z2 non-anomalous global symmetry. Very schematically speaking, I write down this picture. Okay, so this is a torus. This is when I draw the square, this is a torus for me. So I'm computing the partition function on torus. When I write this picture, I mean I'm just computing the partition function of the untwisted sector. Untwisted sector in a modern language means I don't insert any topological operator in my worksheet. This is the untwisted sector. Or you can think of this as just the partition function of the original theory before the gauging. The gauging of the Z2 symmetry means I need to sum over all the untwisted and twisted sectors under the Z2 action. So this is putting a Z2 line on the spatial slice at a certain time. So if you think of this as time, this is spatial direction x. I'm inserting it on a certain time slice, on a slice of certain time, so that it projecting or so that it acting on a Hilbert space defined on this S1. So this plus this with the 1/2 is just projecting on the Z2 even part of the non-untwisted sector. But I can also twist my Hilbert space on S1 by inserting on time direction a topological operator, which is ZG, which is also the Z2 non-trivial element. Okay, so this is another topological line. Sorry, this is the Z2 topological line, but now inserting on the time direction to twist my Hilbert space. And then this picture plus this picture is that I'm using this Z2 action to do the projection on the Z2 twisted sector. In the old-fashioned way, it's called Z2 twisted sector. In modern language, people now prefer calling it Z2 twisted Hilbert space or defect Hilbert space because it's living at the end of the Z2 defect or twisted by the Z2 defect. And this is the result of doing the gauging of the Z2 symmetry. And then you can think of this as into a unified configuration so that every time I just draw this kind of resolution of a trivial injection. So every time I think of I have two lines, this, I use the dotted line to denote the trivial defect. So every picture can be written into the crossing configuration. And then I need to resolve this forward injunction to avoid the ambiguity because because only the trivial injunction is well defined for the fusion category. And then I do this resolution, do this resolution, do this resolution, do this resolution. Okay, this is how I do the gauging. This picture is exactly the same as this one. The anomaly is encoded in the resolution of this picture. So basically you can think of that, oh, I can do this resolution or I can do this resolution. Yes, I can do this resolution. And these two resolutions might be different by a sign. If they are different by a sign, the Z2 symmetry is anomalous. So there's no way you can build a unambiguous sum over twisted sectors so that the Z2 cannot be gauged in this case. So this is what the anomaly means in the Z2 case. And then, of course, for a Z2 symmetry, you can think of a non-trivial gauging, or you can just think of a trivial gauging. I'm just doing nothing. So I'm just gauging of one inside Z2. And of course, this is just doing nothing. So this is the original theory. So it's just the untwisted sector partition function.
Can I ask something?
Yeah.
The first equality really looks like the toric code excitations with some weighting. Is there any relevance with the toric code?
I think you can think of the toric code as the sim TFT, as the, you are saying 2 plus 1 the toric code, right?
No, 1 plus
1 plus 1 the toric code. I think so. I think the toric code is basically just it's just the flow to the Z2 phase, Z2 topological phase, right? I think it's yeah, I think they are very closely connected.
I see, because the resolution looks like
I think those things are more connected to this part, but of course, since these two things are one-to-one components to each other, so you can say that if you have a Z2 toric code which give you some topological phase in the infrared or under the thermodynamic limit, you can also try to redraw this picture.
yes. So I guess the resolving the second equality looks like you hit with some operators in the Hamiltonian of the toric code to the first equalities respectively.
Oh, I see. Yes.
Uh-huh.
Yeah, I'm not that familiar with the lattice model, but I think
Okay.
what you said I think what you said sounds correct. Yeah.
Yeah, I see. But there is also some weighting in the sum, right?
It's 1/2 in this case.
Okay, I see. Thank you.
Yes. So in the field theory perspective, the 1/2 is just trying to build the projector on different Hilbert space.
Yeah.
Right.
Thank you.
Oh, yeah, sure. Okay, now
Can I
let's go
also
to,
ask a question? Sorry.
yeah, sure.
So when we gauge a group symmetry, the quantum dual is like the Pontryagin dual of that group. But if we
Right.
naively gauge some categorical symmetry with some fusion category C, what kind of a quantum dual symmetry we get as a result of this gauging?
It's very complicated. The short answer is you are trying to get the AA bimodules over
Hmm.
C. The A is the algebra object you're trying to gauge.
Oh,
But
okay.
there will be a way, but yes. And in general, you can write a code to find what that bimodule is, but in principle, it is very hard to really do the computation. But there is a
Okay.
notion of the Pontryagin dual for certain gauging of the fusion categorical symmetry. There is indeed a very well-defined procedure. Yeah.
I see. So, for example, in the case of the Tamberi-Megami category for Z, and what kind of dual do we get? Like, is it something simple that we can understand, or is it also complicated?
It's kind of like the Tambra Yamagami for Zn or for some other abelian group. If you're only
Like,
thinking for Zn,
I mean, I'm thinking for the
many of
simplest
those things
case,
are
it could
unknown.
even be Z2.
Yeah, for Tambra Yamagami of Z2, it is anomalous, right? The only gauging you can
Hmm.
do is the group-like subcategory, like the
Okay.
Z2. Consider Ty of Z2. Only the Z2 part can be gauged. But that
Hmm.
Z2 gauging is actually Morita equivalent to the trivial gauging. So you're basically
Hmm.
doing nothing.
I
You
see.
realize you can do the Z2 gauging is basically the same as you realizing you have the Tambra-Yamagami Z2 symmetry because the non-invertible line in the Tambra-Yamagami is the result of doing the gauging of Z2. It is the
I see.
self-dual of the
Mhm.
under the
Okay.
Z2 gauging. Yeah.
Okay.
Okay. So now let's move to the topological world. So there are two things I can think of for the Z2 symmetry, right? I can do the non-trivial gauging. I can do the trivial gauging. For Z2 symmetry protected gapped phase or topological field theory, there are also two options. You can consider a Z2 symmetry protected phase, topological phase, which means I have a unique vacuum protected by Z2. So I use a quiver diagram. This quiver node for me is the single vacuum. And this line means that under the Z2 action, this vacuum is just symmetric under itself or transformed to itself. And if you're trying to build the excitations or the topological configurations, since there's only one vacuum, the only non-trivial configuration you can build is a local propagating particles, right? Because particles are excitations over a certain vacuum. So this link can also be thought of as a particle when you try to build excitation above the vacuum. Or you can have Z2 spontaneously symmetry breaking phase. In this type thing, we know that, if I have the SSB, I should break the Z2 symmetry into two vacua. So neither of the vacuum enjoy the Z2 symmetry. The only way to capture the Z2 symmetry using this TQFT or using this gapped phase is trying to connect them by the Z2 symmetry. So this is what this quiver diagram means. I have a single node here. I have a single node here. They are labeling two vacua, which are exchanged by the Z2 symmetry. This arrow means the Z2 action take this vacua to this vacuum. This line means vice versa. So node are still vacua, that's fine. But this means that if I want to build symmetry protected topological configurations or configurations above this vacua, the only thing I can build is soliton anti-soliton. Okay, so this is a soliton transited from this vacuum to this vacuum. This is the anti-soliton transited from this vacuum to this vacuum. There's no particles you can build because there's no local excitations can be protected by this symmetry. Okay, so how to unify these two things? I mean, I know that for CFT, I can talk about its gauging, its partition function, all kind of things. And as some of you asked about its quantum symmetries, all kinds of things. And in TQFT, I can talk about the representations of the vacuum, right? It can be the trivial representation, right? Because I only have a single element and it is transformed trivially under the Z2 symmetry. Or I can have a non-trivial representation of Z2. So I have two vacuum and then it's like the sign flip, right? This is plus sign. You can label this as plus sign, minus sign, then they're transformed under the non-trivial Z2 representation. That's great. These two things are actually connected or unified in the notion of algebra object. So for every gauging, you can assign an algebra object to the symmetry you are interested in, and that will be a certain gauging of that symmetry. Likewise, for a TQFT or for a gapped phase protected by that symmetry, you can assign an algebra object and look for or derive the corresponding gapped phase or TQFT or topological configuration associated to that algebra object. In Z2, this is very easy. In Z2, you can rewrite the sum over picture into a single picture, which you just label the algebra object on each line. In this case, the algebra object can be 1 plus eta or 1. Eta is the non-trivial Z2 topological line in this case, okay? If I choose this algebra object in this picture, what I'm doing is doing the non-trivial Z2 gauging.
So is this like the ARF twist?
Sorry, what?
Like when you gauge a Z2, you can, put like an ARF twist, and that's the non-trivial gauging of Z2. Does that correspond to the ARF twist rule?
You mean the fermionic SPTR or some other things?
Yeah, the SPT-ARF.
No, in this case, it's just the bosonic theory to bosonic theory. I'm not
Okay.
really
Okay,
doing the
okay.
fermionization. Yes,
Yeah,
but
okay. I'm
fermionization
confused
can be
now.
think of yes, right. Yeah, the fermionization can be think of as first the stacked RF SPT and then do the Z2 gauging. But that will
Okay.
connect it fermionic and bosonic theory. Yeah, okay.
Okay.
So in this
I
talk, I
see.
will just focus on purely bosonic phase, no matter CFT
Okay.
or topological.
I
Yeah.
see. Okay.
But thanks for the question so that I got a chance to clarify this. Or you can think of A is just 1, then this picture will just be nothing. It's just the trivial gauging. It's still the untwisted sector partition function. So it's the partition function of the original theory. Or you can use this to you can use this to algebra object to see what is the corresponding topological configuration. If I pick A equal to 1 plus eta, this is corresponding to the single SPT phase. And this is the very well-known result. If the global symmetry is free of Taft anomaly, which means you can do the non-trivial gauging, then this theory can flow to the trivially gapped phase. In other words, say the other way, if you cannot do this gauging, which means the Z2 is anomalous, then there is a obstruction to the SPT phase. Okay, so for anomalies, usually there are two notions. One notion is, let me write it down. For anomalies, to foot anomaly in all this talk. You can think of that as abstraction to SPT or gauging. And these two notions in the invertible symmetry case are basically the same. They are precisely the same. For the non-invertible symmetry, they are almost the same, but there might be some subtlety there. But let's not go into that now. So this is how you connected the topological world and the conformal world. Here, if you can do the non-trivial gauging 1A equal to 1 plus eta, that means you can build the SPT phase, which means you can build the trivial representation of the Z2 symmetry, which means you can build me particle excitations above the single vacuum. But no matter Z2 symmetry is anomalous or not, you can always do the trivial gauging, which means for Z2 symmetry, you can always build the spontaneous state symmetry breaking phase. So you can always have two vacuum.
Then
build
ask a question.
Yes.
Is the definition of a 't Hooft anomaly its understanding as an obstruction to SPTs or obstruction to gauging is still, does that still hold for higher dimensions like 2 plus 1? I thought it
Uh, I
exactly the same.
I think it's not clear to me because in higher dimensions, like abstraction to SPT can be very different to abstraction to gauging.
Yeah, okay.
So
So
I'm
this
not.
this holds in 1 plus 1 only,
Yes,
right?
yes.
Okay, okay.
In 1 plus 1, this is always fine. Yeah.
All right, thank you.
E- yeah, even in 2 plus 1, the many subtleties happens. Yeah. Okay. Now the question becomes, okay, what is the algebra object we can think of, right? Because now you told me that, oh, in the Z2 symmetry, I'm just looking, I can just translate very unnecessarily, but I can translate it, the gauging and the topological configuration wraps into the language of algebra object. So in general, for a fusion category, which is describing the non-invertible symmetries in 1 plus 1D, the condition of the gaugeable algebra object is actually a special symmetric Frobenius algebra, or sometimes people say that it's symmetric delta separable Frobenius algebra. So I I don't want to really write down the very algebraic condition, but I think the picture it helps sometimes. So it says that you can from a single, so it says that for an algebra object, so this will be a non-simple lines, right? Because algebra object is just a sum over some topological lines. So for the algebra object topological line, it should be able to split into two algebra object lines and then going back to itself. And this should be the same as just doing nothing. And you should also have the associative condition. So in this time, if you want your algebra object to be free of two anomalies so that you can do the gauging, you should not have two non-trivial F symbols. You should have a F symbol so that it is associative. If you don't have that, it will have something like this will happen. You have two different resolutions because this picture going to this picture is just a associator move, okay? But you don't want that happens. So you need to have a associative move. And you should think of this. Okay, for a single algebra object line, you should be able to just create a line from the vacuum or just from the unit operator and then shrinking it by pushing this unit operator into this junction. So basically, it's the same as doing nothing. And you have other pictures, but they're just built by the adjoint or the dual of these pictures. So this is how you define algebra object. I mean, gaugeable algebra object in the fusion category. So stage for today, like what kind of symmetries I want to think of course, there are like infinitely many non-invertible symmetries which described by infinitely many fusion categories. I don't want to do purely mathematical thing. I just want something which is physically interesting for me. So the secret one CFTs give me a perfect stage. In secret one CFTs, you have orbifold, so you have circle branch, which is just labeling the radius of the single compact boson in 1 plus 1D. Okay. And you have orbifold branch. The orbifold branch just means that you are starting from the circle branch, which is describing the compact boson in 2D, and you're gauging the charge conjugation of that compact boson. Let me write down. You have the compact boson X. The charge conjugation is just the reflection of the target space coordinate. And if you're gauging this D2, you are moving to the same radius, but now on the orbifold branch. And it's starting from 1 because I'm also having the T-duality, which just flip the radius of the compact boson, okay? So this 1, 2, 3 means the radius on the circle branch. This 1, 2, 3 means the radius on the orbifold branch. So you'll see the radius 1 of the orbifold branch coincide with the radius 2 of the circle branch. You can find this thing in the very old paper by Ginsberg in 1988 called Curiosities of Secret 1 CFTs. or you can just look at any of the review of the CFTs. You can find this thing. The interesting thing is that if I start with the 1 here, because you see R goes to 1 over R, right? This is the self-dual point. If I gauge in the self-dual point, I have a ADE classification of the gauging. The ADE finite subgroup or non-anomalous subgroup of the SO4, because SO4 is the global symmetry of the self-dual point. It is basically, if you have learned the string theory class, you know that at a self-dual point, you have 2 copies of SU2, but the global structure tells you that you need to mod Z2. Okay, so this is where the SO4 come from. The A is just the Zn subgroup, so it will take you just the 2 different radius of the circle branch. The D is the Z and semi-direct product of Z2, so it will just, that Z2 is the charge conjugation, so this will just take you to a different part of the orbifold branch. And there are 3 exceptional cases. The 3 exceptional cases are given by the A4 finite group, S4 finite group, and A5. A is alternating group, S is symmetric group. By definition, if you gauge non-abelian finite group G, you will have a rep G symmetry. So today we will focusing on this theory, and this theory. And it is known that SU2 at level 1 mod A4, of course, by definition, has at least a rep A4 symmetry. This theory has at least a rep A5 symmetry, and this point, which is the Kostolis-Tholet CFT point, it can be think of as the continual limit of the 2-dimensional XY model. It has a non-trivial triadity defect or triadity symmetry. So I would like to extract the result of this thing. When I say extract result, I mean I want to know how to gauge the symmetries, what are the possible gaugings of these symmetries, and what are the representations of the topological configurations if I have a topological phase in drawing these symmetries. And then you might say that, oh, okay, great, you already told me what to do. Just looking for algebra object and write down the reps associated to that algebra object. Yeah, it's not that easy. It's just always, as all the research project, it's easier said than done. That's why we need phenomenon algebra. That's why we need phenomenon subfactors. Any questions before I go into the technical part of phenomenon algebra? Great. I will be very sketchy and fast in this point because you don't really need to understand every single point of phenomenon algebra to see my result. So let me just very quickly do this thing. So phenomenon algebra is a C-star algebra. It's describing or the object or the element in this algebra are just bounded operators acting on a Hilbert space. Okay, it can be any Hilbert space you like. So you can first think of a set of operators acting on the Hilbert space H. Okay, let's call this B of H, just bounded operators on H. And then for a certain subset or a certain subalgebra A, you can consider its commutant. The commutant, of course, is defined by the A prime, which has all the operators commuting with the operators inside A. So A is a phenomenon algebra if it is closed and adjoint, and it is containing the identity operator, and if you do 2 times of the commutant, you find itself. And the phenomenon factor is a certain type of algebra, so that you have A with A prime has only identity at its multiplets. Subfactors, okay, of course you can just consider the phenomenon factors as you can just consider the phenomenon algebras, and nowadays it has many very interesting physical applications in the lower dimensional holographic world, and also the state of space and the black hole physics as Edward Witten, Jeff Pennington have been done. Now, but today we don't really focus on a certain factor. All the information I need to do the symmetry manipulation. It's a pair of phenomena factors. And the only thing I need is how one factor is embedded into the other factor. This is called subfactor. If you trying to learn some mathematics or heard some talks about Feynman algebras, you will heard this kind of half joke, half thing like the Feynman algebra is not algebra, it's actually analysis. But Feynman subfactors are algebras. So you can think of pair of factors N and M. In this case, I take type 3, but type 2 is also working. It's just a different. If you are interested in different, I think for the physical application, type 3 and type 2 in this case are both fine. It's just your preference. Let me just work in type 3. So N sub M with a certain embedding delta. So embedding N into M. This information is called a Q system in phonema subfactor. So after you build this language, after you build the subfactor, skipping all kind of technical result, the information as output for you is a fusion category C as the category of certain endomorphism of N. And the embedding delta gives you the algebra object A, gateable algebra object A in this case, of the fusion category C as delta bar delta. And you can also extract A modules. So modules in mathematics in many senses, it means the same thing as repetitions, okay? So basically when you know the A modules, you already know what is the repetition associated to the algebra object A of the fusion category C. If this is too abstract, you can think of C equal to Z2. You can think of A equal to 1 plus eta, and this A module is just the trivial repetition of Z2. Or you can think of this is Z2 and A is just the trivial, and then A is the trivial algebra object, and then this A modules will give you the non-trivial Z2 repetitions, which have two nodes in the quiver diagram. So this wraps as the A modules over fusion category C. From the subfactor language, this is the NM bimodules. The picture is looking like this. The picture is like this. I can have a subregion or a region of the 2D space-time. I can build you the algebra object, okay, and stopping at a defect. And then this object A can be thickened into delta bar delta by definition of the Feynman algebra, okay? Because I'm building you the embedding, which is labeled by delta. And then I can have you, and then I can give you delta bar delta here. The inside shadowed region, smaller shadowed region, is M, and the outside region has the Feynman algebra or the Feynman factor N. And then you can do similar things. You can do similar things like this. You can do similar things to build all kind of picture you like. You can build this picture. This picture is equal to the thickened part, like the shadow part is always the N. I build it from deforming the NM bimodules or deforming the delta bar from the algebra object A. This is equal to this one, which is also equal to this one. And you can also build this picture. You can also have this picture. You can have this, and you can have this, and you can have this. This is also the shadow region. This picture is the same as this deforming. Just have this, and you have this. You can do this, and then you have the shadow region here. And then you can keep deforming it. You keep deforming it so that you have this. And you can do the similar, just the graphic game. You will find out that this reproduces exactly the delta separable symmetric special Frobenius algebra structure. So you start with the fundamental subfactor, which give you the embedding of delta, and you build the algebra object A as delta bar delta, and then you just deforming the NM by modules. And by doing all kind of deformings from different starting point, you can recover all the conditions of delta separable symmetric Frobenius algebra, which means given a subfactor, I'm actually talking about a certain gauging of a certain non-invertible symmetries.
Can I ask a question?
Yeah.
So, should we think of these shaded regions as some topological defect or like the
Yes, yes.
boundaries of
In the end,
these?
yes, great. Yes. In the end, you can just think of these shaped regions as just the algebra object A.
Hmm,
You,
I see.
you can just going back to the thing, you can just make all these shaded regions thinner and thinner so that you just write down the topological operator,
Hmm,
which, sorry, you just write down the non-simple object labeled by the algebra object A, and then you just recover the gaugeable algebra object conditions.
I see.
Yes.
So, is this like the categorical analog of the, network of defects that people use when they are trying to gauge some Z-and symmetries? Like, is it something like that, or is it different?
Sorry, what network are you referring to? Are you
Like,
referring to the
I'm
tensor
not exactly
network,
sure
the
what.
math model, or?
Yeah, like, people talk about when they try to gauge some Z-and symmetry, there is some network of defects that they insert into the partition function, and then summing over these network of defects, by
Yeah,
some
right.
Poincare
No,
duality and so on.
yeah, that's not exactly the same thing, but these conditions
Hmm.
are ensuring that sum over is making sense.
Okay.
Like, let me go back to the partition function here, right? So this is the thing you are saying. This is just the summing over all the Z2 topological line insertions.
Yeah, I guess so.
And
That would
to
be
make
like the
sense of
network of
this summing over,
defects.
yes, yes, right. To summing over, so to make sense of this summing over, you need to, sorry, to make sense of this summing over, you need this picture to be the same as this picture. You need these two
Ah.
resolutions of this picture being the same.
Hmm.
And this condition is translated into the delta separable symmetric Frobenius algebra. And
I
then you
see.
recover all these conditions from the phonemic subfactor delta bar so that you can build M
Okay, I
as
see.
the inside shaded region of N. And then you can just deform N by modules as A modules. And then you thinner the picture again, you recover the gaugeable algebra object condition. Yeah,
Okay, okay, thanks.
no problem. Okay, so but if I just keep drawing the picture, that will be too hard to really do any computation, right? I cannot really check what kind of picture I can draw, what kind of thing I should be writing down. So is there a quicker way to do this? The answer is yes. So a very nice illustration of the phenomenon subfactor is the principal graphs. Let's just consider the 2D, let's just consider the Z2 case. The principal graph has, let me first draw the picture and say what I mean by different things. All right. I can have this is one, this is, and so on. Or I can have this. The red dots are called even parts. The black dots are called odd parts. And this principal graph are always bipartite. It means every even dot is connected to a odd dot. Like you cannot connect it different odd dots or black dots, or you cannot connect it different red dots. Okay, so even part connected to odd part connected to even parts. So even part, they labels objects in fusion category C. Odd parts, they are labeling, okay, let me call this objects of this. The odd parts connecting, oh sorry, it's labeling the objects of the module category or the representations of the fusion category associated to the algebra object A. So in this picture, I'm actually taking A equal to 1 plus eta. So based on this algebra object, there is only a single representation, or there is a single odd part of the principal graph, which is this. And it's connecting both even parts. So this singlet means under this algebra object, I'm doing the non-trivial gauging. Equivalently, it means that associated to this algebra object, I'm considering the trivial representation of Z2. In this picture, this is corresponding to the trivial gauging or the trivial algebra object of Z2. So there will be an odd part, like there are always a odd part labeled by the algebra object, and it's connecting to the algebra, and it's connecting to the even part is just labeled by this. So I have 1 plus eta, so I should have an odd part class to 1 connected to 1 and eta. I have A equal to 1, so I should have an odd part connecting to this. And there is some technique you can do to compute what is the other thing is. And then after the computation, you find out that there is single other black dot here, and then connecting to the eta. You have 2 here, which means that this is the non-trivial representation of Z2. And you can see the representation because you can label this by 1 plus eta. And you can acting on this 1 plus eta. You can use the eta acting on the 1 plus eta. In the end, you will have eta plus 1. So this is the same as this, which means this representation is invariant under the Z2 transformation. You can also label this odd part by the even part it connects. And then you would say that if I have eta acting on 1, it will become eta. Eta acting on eta, it will become 1. Let me use the black and let me try to do this. This is the even part acting on the odd part. This is the even part acting on the odd part. This is even part acting on the odd part. You see, the even part, the topological line, acting on this black dot, which is one of the repetition, give you to another repetition here, which means this black dot is transformed into this one by acted by eta. And of course, you can do similar things, which means this eta transformed to 1. So you can build quiver diagrams. The quiver
Can I ask something
Yes?
Can I ask something before? Okay. I think if I understand correctly, we can reconstruct the fusion rules and algebra multiplication explicitly, given a principal graph, right?
You can build the
I mean, if we have a principal,
it has the information of fusion rules, yes.
Okay.
Yes, but the F symbol is somehow implicit. It's not it's not really directly readable from the principal graph.
Okay, thanks.
Yeah. Then you can build quiver diagrams, right? Because for each odd part, you give me a quiver node, and you just write down how it is transformed under the even part. This is this example, or I can have this. I have one eta. I can have this, this. And this means they're connected or they're transformed under the eta. Oh, sorry. Yeah, I don't need to revisit Z2. Sorry, I already used the Z2 as the example. So this is basically how the phenomenon subfactor tells you the information you need. So the main results we have is basically like this. The main results, oh, sorry. I think my MacBook is almost out of charge. It still have 18. Okay, so it should be fine. So the main result we have is the first one is necessary conditions for A. So given me a fusion rule, I can try to solve all possible principal graphs. If given me a fusion rule and a expected algebra object, but I cannot find the existing principal graphs, then that means I have to exclude that gaugeable algebra object. The second thing is basically just given an algebra object A, given an algebra object A, I know its reps, especially for topological configurations. Because after I computed the principal graph, I can just compute the quiver diagrams, labeling how the odd parts are transformed under the even parts. Once I do that, I give that quiver diagram a physical interpretation, right? Because this quiver diagram and this quiver diagram, you can just don't write this, don't write this, don't write this, just don't write eta or 1. This is exactly how the Z2SPT phase and how the Z2SSB phase are seen. And this single line is exactly telling you that there's only particle can be excited in this case. And these two lines are telling you that you have soliton and anti-soliton pair. So these are our two main results. And of course, this is somehow, in some senses, better than the conventional very fusion category or tensor category language, because it is very schematic. You can see it very quickly. The necessary condition, if you just you can just write down some codes saying that I have this kind of fusion rules, find the principal graphs for this certain algebra object, and then you can do a very complete exclusion. And you can find all possible algebra objects for a certain fusion rule. And then, of course, on top of that, there are some information about F symbols, which is implicit for the principal graphs that we will just leave for future work. But very luckily, for the symmetries we're interested in today, like the triaded defect, rep A4 and rep A5, you can have the complete answer. Okay, so let's consider the triaded symmetry. Oh, sorry. Before going to the examples, any questions so far? Okay. Let me remind you, the triaded symmetry is on this point. Okay, so how do you get the symmetry? You start with the SU2 at level 1, and then you do a Z2 gauging. This is SU2 at level 1 mod Z2. You do a Z2 gauging and you end up with this tragedy effect is because if you consider the A4 symmetry, the A4 is a subgroup of SO4. If your theory has an A4 symmetry and you do a Z2 gauging, the dual symmetry will be this tragedy defect. Okay, so this is a very non-trivial result of quantum symmetry. So in principle, for abelian symmetries, you have a gauge Zn and I have a dual Zn. So in this case, like I know in this theory, I have a SO4. Let me focus on its A4 subgroup. And I'm gauging the Z2 inside of this A4. What is the dual symmetry? The dual symmetry is this triadyl defect. So this triadyl defect has the following fusion rule. It has T times T. It's 2 times its adjoint, or you can think of this as orientation reversal in the physical perspective. And then you have T times T bar. It's sum over Z2 times Z2 element, okay? So this is an extension of the Z2 square symmetry. And this is the non-invertible triadyl effect. This is the orientation reversal of that triadyl effect. And then we use the principal graph to find all possible gaugings of this symmetry. The result is like this. You have 2, you have a SU2 at mod A4. This is the KT point. You have 1, 3 here. So you can do different kind of gauging. You can do this gauging. The result is 1 plus eta prime here, or 1 plus eta prime. Okay, this is gauging 2 different Z2s inside of triadyl symmetry. And you find out that this is just going along the orbifold branch. Or you can do another group-like gauging, like 1 plus eta. This 1 plus eta can be think of as the dual gauging of the original Z2 gauging, because originally I start with this point and do a Z2 gauging, go to this point. So there should be a dual Z2 gauging so that I'm going back. This is the dual Z2 gauging. And then there are some other gauging. You also have this kind of gauging. This is a little bit tricky. This is 1 plus eta plus T bar. So this is certainly a non-group-like gauging, right? Because it has non-invertible symmetries here. You have this type of gauging. And you also have this gauging. Go from here to here, you have 1 plus eta prime plus T bar. You have 1 plus eta prime plus T bar. So this is the result you can find out by looking at these fusion rules and compute what is the principal graph you can have. The rep A5. The rep A5 is more complicated because in this case, we need another notion of dual principal graphs. Recall the definition or recall something about the phenomenon subfactors, okay? I can build Mn by modules by looking at the Yalta bar construction, right? So principle speaking, I should also be able to build Nm by modules. You can think of Yalta as Mn by modules, and then you can think of Yalta bar as Nm by modules. And then in the end, Yalta bar Yalta give you A. So basically, you should be able to think of that I have the repetitions, which is module categories. Very abstractly speaking, I have repetitions, which is labeled by C of A. This is corresponding to Nm by modules. I should also have Mn by modules. And what is this corresponding to? What representation this is corresponding to? This is actually the left module. So this is basically the right module. Means that I have some fusion category symmetry C, which have some topological lines here, the LA, and then I have some interface or topological boundaries here, or some other boundaries here. I labeled this thing by the M of let's say M of I. So this is one of the representations or one of the object in the module category CA. Okay, and then I have LA transforming this MI into some kind of MJ. I can build this kind of junction. So the equation you can write down is LA act on MI is just the sum over MJ C A I. Sorry, C A I J L J sum. So in the case of Z2, this is very easy to understand, right? Because this is LA is just given by my eta. This is just given by, it can be 1 plus eta, or it can be 1, it can be eta. It depends on what algebra object you're looking for. But this equation is just rewriting how the principal graph is telling you the odd part are transforming under the even part. The interesting thing about the bimodules is that since for every gauging of a fusion category, there should be a dual fusion category, and there should be a dual gauging of the dual fusion category so that you go back to the original fusion category. This coincides with the fact that as long as you can build me n bimodules for a subfactor, there should be naturally a notion of n bimodules, and these two things are connected, are one-to-one correspondent to each other. But what is the principal graph information of this? This is actually the n bimodules, as I said, is the odd part. And then this thing should be the dual odd part, which means I can have some principal graph which has very complicated connection on different lines. Then there should be a dual principal graph whose odd part coincide with this principal graph. I can have a very crazy dual principal graph, which I don't know what I'm drawing, but the picture is something like this. So they look very different. Okay, they look very different. So they have different even part, which means, so this is a principal graph. This is another principal graph, but I just the reflection, the left and right of the left of the even part and the odd part. Okay, so this even part are labeling the fusion rules or the fusion category information, and this black dot for this principal graph is labeling the repetitions of the repetitions associated to CA of the fusion category C. And this dual principal graph is labeling the repetition of the dual fusion category C under some algebra object A prime, but it is simultaneously labeling this thing, which means A module category of C, if given you an algebra object A, you can find the repetition of the fusion category C. That repetition has to be also the repetition of the dual fusion category, of the dual symmetry after gauging. Because n bimodule is one-to-one correspondence to n bimodule in the phenomenon subfactor, which means the two principal graphs, if they are dual to each other, you have to be able to glue them together along the odd parts. Since odd parts are repetitions, which means I should always be able to determine the repetitions of the dual fusion category if I know the original repetitions of the original fusion category. And this is how we compute the rep A5. So for rep A5, I know all its gauging, I know all its subgroup H of A5. Use the group theoretical information, I can find out all the repetitions here, the dimensions of all the repetitions, labeling by the H module inside A5. And then I can try to find rep A5 because I know the rep A5 should be some part of here, right? The rep A5 is is the result of gauging an A5 symmetry. So there should, for each gauging of A5, there should be a gauging of rep A5 so that I can glue the principal graph together. And I do this gluing because I know, based on these gluing constraints, I know what the dimension of the repetitions should I have for the given algebra object of rep A5. So in the end, let me just show you the result. Oh, sorry, I think my laptop is almost down. Can I just pause for 1 minute to
Yeah, of
give
course,
it
of
some?
course.
Yeah, right. Yeah, sorry about.
Gordon? Okay.
I'm sorry. I cannot find the long enough line. Okay. So you can try to find all kind of gaugings of rep A5 by by solving its possible principal graphs and see if it can be glued by the it can be glued without out part to all type of A5 gauging. Okay, so all the result we have is it's like the result is very complicated, but let me just show you the pictures very let me just show you the pictures very quickly. Like I won't be able to draw all the pictures, but let me just copy the pictures in our work. So basically what you have is, so what you start with no, this one. What you start with is this picture. So this is all type of gauging of A5, right? I start with SU2 at level 1 theory, and then I do all type of gauging. Of course, A4 is one subgroup of A5, so you should also think of that type of gauging. And then you compute all type of gaugings of the A5, and then you compute what's the dual symmetry of that. And of course, what we're focusing on, what we're interested in is to find the gauging of this theory. The result we find is that the gaugings of the rep A5 is here. All the gauging of the rep A5 is in this picture. Okay, so the starting point is always this line. And you can gauging all kind of algebra object. So here, the x and x prime are three-dimensional repetitions of rep A5. Sorry, this three-dimensional repetition of A5. So it's a three-dimensional object in rep A5. And we have U, it's 4-dimension, V, it's 5-dimension. The interesting thing is if you consider a certain gauging of rep A5, you find out that this exceptional orbifold CFT can be self-dual under gauging. There are 4 self-dual gauging you can think. It's 1 plus S, 1 plus X prime, and this and this. Self-dual gauging means what? The self-dual gauging means if I start with the theory T, I gauge the algebra object on half of the space-time. And then I can think of two topological interface between these two things. Okay, but the self-dual means after gauging, I have the theory as the original one. So this means that this topological interface, separating two different theories, is promoting to a topological defect of a single theory. So once you find a self-dual gauging, it means you are extending, you are finding the enhanced global symmetry. And the fusion rule of this thing is very similar to the Yalta-Yalta bar construction. Okay, in this case, you can call this n, you can call this n. What you have is n times n equal to the algebra object A. Because you can think of squeezing this region. Okay, inside this region, you're summing over all the topological lines labeled by A, or you are just inserting these topological configurations, the network of lines, right? And then you're squeezing this region. In the end, you will have this kind of picture. You have T here, you have T here, and you are summing over all the lines on this line. So this is the condensation defect, which means if you fuse n with n, in the end, you will just have the algebra object labeled by A. Of course, A is sum over something. So in the rep A5 case, in the exceptional CFT case, I find 4 self-dual gaugings, which means I should think of 4 other topological defects or topological lines at this point. With the fusion rule, let me call this n times n, n1 times n1, 1 plus x, n2 times n2 is 1 plus x prime, and also for these two other algebra objects. So in the end, you should including 4 other topological defects into the rep A5 symmetry. And what is that symmetry? You can check the fusion rule, okay? After we check the fusion rule, that is actually the symmetry of rep SL2 Z5. So originally, we start with a rep A5 symmetry on this exceptional orbifold CFT. But we realize the self-dual gauging by looking at all possible rep A5 gaugings. And we find out that, oh, there are 4 self-dual gaugings. And then we include the extra topological defects into the rep A5 global symmetry and check what is the fusion rule for the new bigger bigger non-invertible symmetries. In the end, we find rep SL2Z5.
Can I
And
ask
if you
something?
know, yeah, right.
So, for example, if you consider the 4D angles with SUN gauge group, we have the ZN1 from symmetry, and from the SimTFT, we find that all global variants of this theory are captured by SL2ZN. And then now you're here considering A5 gauging, and then SL2Z5 appears. So does this mean like we are somehow finding all the global variants of this, theory with the C symmetry?
You can think of in that way, yes. You can think of like from this theory with A5 globe symmetry, you do all possible subgroup gauging like this picture. You can think of every point is one of the element theory in the global variance of the group.
Okay.
Like in this case, it is called orbifold group, right? But you can just think
Okay.
of, you can try to capture, you can try to write down all the theories connected by gauging of a certain global symmetry. Yes, and then you can
Okay.
do that. And then the interesting
So,
thing is that the gauging is always invertible. If you can build the picture from this theory, you should be able to build the picture also from this theory. And the interesting point is how to classify all the rep A5 gauging for this theory.
I see. And that comes out of like SL2Z5, the rep of SL2Z5.
Yes, yes,
Okay.
yes. Yeah, the SL2Z5 is actually the Z2 extension of the rep A5 because you find
Okay.
the self-dual gauging at this point. So you know the rep A5 cannot be the full global symmetry of this exceptional orbifold CFT. You
Okay.
have to include extra topological defects. Let's say you consider the Ising CFT. In Ising CFT, you can say that I'm innocent. I'm only focusing on the Z2 symmetry for me. If you only know the Z2 symmetry of Ising, but then if you know how to compute the partition function, you will see that, oh, actually something happens. The Ising is actually the same as Ising mod Z2. If you do that, then this is Ising for you. This is Ising mod Z2, but it's also Ising.
Yeah.
And then you can end up with a new topological defect, which is n times n equal to 1 plus eta. So you know Z2 cannot be the full symmetry of Ising. Sorry, you know it cannot be the full symmetry. What is full symmetry? The full symmetry is temporal Yamagami of Z2. So this is just a more it's just a more non-trivial example,
I see.
but under
Okay.
the same philosophy of how you build Kramer-Weiner symmetry for Ising CFT. Yep.
So yeah, essentially it's like finding all the global variants, and it's an extension of these, simple examples. What you're doing
Yes,
here.
exactly. You find all the global variants, and there are some fixed point under the gauging. As
Okay.
long as you find a fixed point under the gauging, that fixed point theory in the global variants should have enhanced symmetry. The way you build enhanced symmetry is to including all the topological defects come from the self-dual gauging and complete the fusion rule. And then you will know what is the theory. At least you will know the fusion ring of the resulting enhanced global symmetry. Yes, in this case, it's
Okay.
just a rep at 2C5. Yep. So very schematically speaking, you can write down something like this. You have rep A5. This is be extended into rep SL25. Let me just do it lazily, just use 5 instead of Z5. And then you can build a rep Z2 here. Build a 1. Of course, rep Z2 is basically the same as back Z2. Or it's just like Z2 is its own Pontryagin rules. Rep Z2 is basically the same as a Z2 symmetry. So this is why the extension works. And of course, after you're building all the principal graphs, you can try to capture all kind of particle and soliton things. But in the non-invertible symmetry, the interesting thing happens because let's just give you one example. Sorry, rep A5. So there's a very let's just consider one of the self-dual gauging. Okay, under the self-dual gauging, you can think of how the X operator acting on different representations. So if you draw the principal graphs, you can find the result in our paper. You find out the quiver diagram looks like this. You have 4 quiver nodes. The X can transform like this, this, 2 lines here. This means if I have a topological face with a rep A5 symmetry, and that topological face is associated to the 1 plus S algebra object, and then the representation theory for that topological face, or the representation theory for the module category of 1 plus X over rep A5, give me 4 vacua. Interestingly, these 4 vacua are not purely connected just by exchanging or by transforming to itself. The transformation rule is mixed. Okay? Sometimes the vacuum can be transformed into itself, but sometimes the vacuum can be transformed to each other. recall our interpretation of these lines or these links in the quiver diagram. These are particles. These are solitons. This is actually telling you that if you want to preserve the symmetry of this topological phase, while you still want to build local excitations and topological configurations above this vacuum, you will have particle-soliton degeneracy, which means if you find out a concrete example, which let's say a lattice model which flow to the infrared has a rep A5 symmetry in continuum limit. And then you'll find, oh, what is the local excitation of the part? What is the particle excitation of local vacuum, or what is the soliton configuration? What you will find out is the particle mass will always be equal to the soliton mass because they build U multiplets under a certain symmetry. Okay, they under the same class of repetitions of the certain symmetry. And this is very early first to find out by some logical in a certain example, but last year, Cordova et al., they repackaged this information into the module categories of fusion categories, and they find this particle-soliton degeneracy. But what they do is always focusing on, they are limited to just, as far as I understand, they're limited to just the trivial algebra object. So they're always considering the fully spontaneously symmetry breaking phase for a certain non-invertible symmetry. But what we're doing in this paper is, since we classify all the algebra objects so that we classify all the repetitions of the non-invertible symmetry, so that we classify all possible particle-soliton degeneracy phenomenon. Or you can see that we classify all the repetition theory for solitons of the topological phase of 1 plus 1D system. That's what we have. And I think I'm way more out of time, so let me just doing a very quick outlook. The question one I have, is there a very quick way to retract the F symbols of the fusion category from the fundamental algebra? Another question is, for C larger than 1 CFTs, what can we say from the fundamental algebra or the fundamental subfactor language? The third question is, I would like to have is concrete examples of particle-soliton degeneracy with non-trivial algebra object we have found. Thank you for your patience. Thank you.
Okay, thanks for this nice talk. Let's have some questions from the audience.
I cannot see the. Oh yeah, okay. Oh, I thought there are some questions in the chat. Okay, so it's not.
Okay, let's wait for. If no one has a question, maybe I can ask one. So if I understand correctly, gauging in this categorical version is just like choosing some, subfactor A, just some sort of like a Frobenius algebra, and then with this, we define some modules in categories, and then
Yes.
with that modules, we understand the dual, like essentially the quantum dual symmetry of gauging
Right.
A.
Yes.
So then the defects of the dual theory would be captured by something like, we have CA in the right and on the left, and I guess it would be like, I think there was something like ACA in some papers in
It's the
QCD
yes,
too.
it's the AA by modules. Yes, I didn't go into details there because I don't really use the result. But yes, the dual category is basically just the AA by modules.
Okay, so I was wondering if there are any applications of these von Neumann subfactors to adjoint QCD, like true bosonization and fermionization.
Oh, right. I'm not sure how to use this in the fermionic system actually. But if you first do the Bostonization, then I think it should be fine. You just ask what is the field and categorical symmetry of the bosonized theory, right?
Hmm.
And then you can just pull this, and then you can just turn on the machine or turn on the toolkit, put the fusion rule inside, and then output it just give you all kinds of principal graphs. You exclude the things which is not really the principal graph, and then you capture all kind of algebra objects. And then you can check what's the repetition, what is the particle-soliton degeneracy phenomena, what is the gauging you can do for the
I
phase.
see.
Yeah.
Okay.
So this is more like the toolkit. So previously people used the phenomenon algebra or the phenomenon subfactor to consider the local information of the QFT, right? Because they are focusing on the local VOAs of CFT or the very AQFT stuff. They're just focusing on the local observables. But for us, I think it's I'm not sure physically speaking is direct connection or not. But for us, this is basically just a toolkit to extract the information of the fusion category, and it's actually very convenient to be used compared to the conventional fusion categorical technique, I would say. Yeah.
In the literature, did anyone try to connect the, holography ideas and these ideas in the fusion categories of
Not
von
really,
Neumann
because
algebras?
because as I said, the holography use fundamental algebra. So for them, the most important thing is for a certain algebra, what is the property? For us, is the pair of phenomena factors.
I
How
see.
one factor is included or the inclusion, the inclusion of one factor to the other is important to us. That's why I said that if you consider a single phenomenon algebra, that it's more like a analysis problem. But if you consider a pair of algebra, or sorry, if you consider a pair of algebra, in particular a pair of factors, and how one is included in the other, then that's a algebraic problem. That's why it
Okay.
can be used to talk to investigate the algebra structure of topological operators in QFTs.
Okay, I see. Thanks.
Yeah, thanks.
Any other questions?
Maybe I can ask a quick question.
Yeah.
So, Burak, can you unmute?
Sorry.
So we have now the necessary conditions for gaugings. I was wondering if they are
Yeah.
also sufficient, or are there any counterexamples where conditions hold, but we cannot gauge it physically?
Yes, yeah, there are actually examples. So one of the interesting example is if you consider the Ty Z2 times Z2. So if you're only looking at the fusion rules, you will find many kind of gaugings. But now we know that for TYZ2 times Z2, there are actually 4 fusion categories corresponding to the same fusion rings. Some of the fusion category has less gauging than the others. Let's say let's consider 2 examples. We have rep H8 or rep D4. Rep D4 is the order 8 dihedral group. Rep H8 is the repetition of the 8th order half algebra. So this has less number of gaugings than this. But if you're just looking at the fusion rings and compute the principal graphs, you will find all possible gaugings, but some of gauging are not working for this one. Those cannot be seen from the principal graph. That's why I said that F symbol seems implicit from the principal graph perspective, and that's also the reason why this is one of the outlook I would like to see.
Okay, thank you.
Yeah. Thanks.
Any other questions? We also take some questions after stopping the recording, so maybe I can stop it now if no one else wants to ask a question on record. Okay.